My dear students, welcome to the new topic which is chapter number 12 from Arfkan on Legendre functions. I will also consult my notes, which you can get a copy from the photocopy shop outside the department. However, I will also show the consulting pages of my notes over here during the lecture as well, but they may not be very clear, so you must get a copy from the photo shop. Okay, now this is chapter number 12, Legendre functions. Legendre polynomials may appear in many different mathematical and physical situations. They may originate as solutions of the Legendre differential equations, which we have already encountered in the separation of variables. So remember that I told you that Bessel's differential equation is the most common equation in physics, and the next common equation is the Legendre differential equation, which we have already solved, and you can see the solution from any standard book, the series solution on this topic. Helmholtz equation and similar differential equations in spherical polar coordinates, they may enter as a consequence of Rodrigues formula, which we will study here. They may be constructed as a consequence of demanding a complete orthogonal set of functions over the interval. Okay, now let me switch over to the pages of my notes. Where are these pages? Okay, this is page number 1 from my notes on chapter 12. Here, let me magnify this. Okay, so here is the Legendre differential equation of order n, 1 minus x square y double dash minus 2x y dash plus n into n plus 1 y equal to 0. And the solution of this equation, the series solution, you may have solved this equation, but if you have not yet, then you can consult Gupta or Pipes' book by Mathematical Physics by Pipes to reach to this solution of this differential equation. Y is equal to a naught, and this is the series with even powers of x, and then another term is plus a1 and is an infinite series with odd powers of x. So you can see the proof at pages 799 plus 780 from the book by Pipes, or pages 762 and 763, which is the Advanced Engineering Mathematics by Jaggi. Now if you look at this solution carefully, there are two parts here, both are infinite, but at one time n can be odd or n can be even. So if n is an integer, one or the other of the two series will terminate. For example, if n is a positive even integer, then the first series will terminate because this contains the even powers of x. So obviously when n is even, you can look at various terms. In this third term we have n into n minus 2, and in the next time we will have n into n minus 2 into n minus 4. So say if n is 4, then obviously the next term will terminate, and similarly the other terms will also terminate, which will mean that the first part of our solution will be a limited series, a finite series, which we call the polynomial. However, the second part will remain infinite, and we can discard the second part in this situation, because our differential equation is homogeneous, which will mean that this part is also a solution and this part is also a solution, and the sum of these two parts is also a solution. So if we discard the second part for n is equal to even, then we can get rid of this second part, and we can contain our solution to only the first term. And if n is odd, then this will be other way around. Obviously the first series will continue as an infinite series, and the second series will terminate at a certain stage. So in this case, the second part of the solution will be a finite series, and the first part will be an infinite series. So we see that one of the part is a finite, which we have named as Legender's function, Legender polynomial, and this other part, which is infinite, we call it the Legender function. So we will restrict ourselves to the finite part, that is the Legender polynomials. Okay, this is what is written here, and you can go through this, what I have said already. And let us now move to the next page of the notes. This is the next page, and if I put this in this form, so this is the okay. Now as I said, that in our solution we will take up the finite part as Legender polynomial, which can be the first term or the second term, depending on n is even or n is odd. Now this limited or finite part, which we call the Legender polynomial, will be represented by this symbol p and x, and the value of p and x we will see in a moment, that this is given by this finite series, whether n is odd or even. So note here that the series written in the is in the descending powers of x. So this series can also be expressed like this by equation A, that is p and x is equal to sigma k from 0 to n over 2 bracket. I will explain that what does this mean, n over 2 bracket. This means that this bracket will always be an integer. So if n is even, obviously n over 2 will be integer, and that will be the value of this n over 2 bracket. But if n is odd, then obviously n over 2 will be a fraction, so we will put this as n minus 1 over 2, which will make it an integer. So if n is even, then we will take n over 2 bracket is equal to n over 2, and if n is odd, then we will take the n over 2 bracket is equal to n minus 1 over 2. Okay. The other series, which is infinite, and I told you that this series is termed as the Legendre function. Now that has been written here as Qnx. So this Qnx is a Legendre function, and we notice that our solution consists of, the total comprehensive solution will consist of a Legendre polynomial Pnx and a Legendre function Qnx, and we can say that the general solution is C1 Pnx plus C2 Qnx. Okay, next page of my notes, which is this one. So here I have expressed what is a formula which is known as the Rodrigues formula for Legendre polynomials. This is Pnx is equal to 1 over 2 power n into n. Let me magnify this. So it is 1 over 2 power n factorial, nth derivative of x square minus 1 power n. The utility of this formula is that we can find Legendre polynomial of any order, which will be this of order n, which will be the solution of the Legendre differential equation of order n. This is known as the Rodrigues formula, which we will derive shortly. Okay, the next page of my notes. So what we are doing on this page is that we are deriving the generating function of the Legendre polynomial, and this is the generating function. Just like this, we had generating function for Bessel's functions. Now we have a generating function for Legendre polynomials, given by g function of t and x is equal to 1 minus 2xt plus t square power minus half, and we will show that this is equal to Pnx summation series Pnx t power n, and this is the generating function of the Legendre polynomial. So in the following portion of this page, this generating function is being established. So we take 1 minus 2x2 plus t square power minus half and write this like this, and then we use binomial theorem, binomial series to expand this. We have bracketed the last two terms here, so we have applied the binomial expression that 1 minus x power n is equal to 1 plus nx, etc. So you can see that this is the binomial expansion of this function, and this is written by this series. This is an infinite series, so we have, sorry, this is the, yes, Okay, so you can follow these following steps and reach to this equation, that 1 minus 2xt plus t square is equal to this. And in the next page, let me go to the next page if it is available. No, I have to go to the next page manually. Okay, so here again the so this is page number 4, and if I put it upside down, it looks like this, and you can see the rest of the steps to reach this expression, that gxt 1 minus 2xt plus t square power minus half is equal to summation p n x into t power n. So we see that this turns out to be gxt equal to 1 minus 2xt plus t square power minus half, turns out to be the generating function for Legendre polynomials, because this single function contains all the Legendre polynomials, as you can see here. Okay, now going to the further next page, which is this one. This is page number 5 I want to display. Okay, this is page number 5. Let me put it upside down. This is page number 5. And here we have, now we are going to derive the Rodrigues formula, which we have done here, and which is this one, Pnx is equal to 1 over 2 power n factorial nth derivative of x square minus 1 power n. So you can see the proof of this derivation from the notes of my pages, from the pages of my notes. Okay, so what we have done so far, we have stated that the Legendre polynomials are the solutions of the Legendre differential equation, which is the next common equation in physics, and we have discussed one or two properties of this polynomials. Okay, let me stop here, and we will take it up the next portion tomorrow in our next lecture. So you can go through the pages by Orcon, the first page of this chapter only, and then you can go through the first 5 pages of my notes. So go through these pages and try to digest what is written here, and try to derive and make up your own notes so that you can fully understand all these steps. Okay, thank you very much.